In this section, we're going to go through and we're going to see another way to solve these systems of equations. But this method is going to be a more general method. So it might seem like it's going to be tedious for those 2 variable systems and 3 variable systems, but this method is going to work way better when you have more variables or more equations, because it can be really tedious to work by hand when you've got 4, 5, or 6 variables. So we're going to work with something that's called a matrix. So an m by n matrix is a rectangular array of numbers that has m rows and n columns. So you're going to indicate with these brackets that you've got a matrix and you've got an array, so you've got a list of numbers in rows and columns. So there's going to be m values this way, and there's n columns this way, so n values in each specific row. So we can use matrices to really represent our previous systems of equations. And the great thing about it is it's going to eliminate that variable there. Each of these columns is going to represent a different variable, and then each row represents a different equation. So what I'm going to do is I'm just going to look at these coefficients, and then I've got this constant term on the other side. So this first equation tells me there's 1x, negative 3y's, 1z, and then 4 is our constant term. If I go through my second equation, I've got 2x's, 1y, negative 7z, and that equals 0. The last equation is negative x, 1y, plus 1z equals 1. So each column represents a different piece. The first columns are our coefficients of x's, then our coefficients of y's, coefficients of z's, and our constant term. And this bar is really representing where that equal sign is going to be. So anytime you want to write this augmented matrix from your system, make sure you have that constant on the other side and things are in the appropriate order. If you've got x's and y's in different spots in each of the different equations, you want to make sure they're going to the same spot in that matrix. You don't want to mix those up. So with this, we've got those different ways that we solved the equations, and it led to a single answer potentially, or multiple answers, but it never changed the solution. So if you took one of the planes or the lines and you multiplied it completely by a constant, didn't change the system. So those correspond to what are called elementary row operations. So we're going to have 3 operations that will yield an equivalent matrix. First thing you can do is you can always change 2 rows. Doesn't matter which equation you write first versus second. They're still just an equation. Second thing you can do is you can always multiply a row by a non-zero constant. So if you got x plus 2 has to equals 4, if you multiply everything by 7, doesn't change that underlying line. So I can do the same thing with a row. The last thing is going to help us with that elimination. So we added one multiple of one equation to another to eliminate a variable. Same thing can happen here. You can add a multiple of one row to a different one, and that becomes your new row. So let's kind of get into what this actually looks like in this matrix form. So we're going to find R3 plus 3R1 yielding R3 for this following matrix. So what the symbol represents is telling us we're going to take row 3, we're going to add to it 3 times row 1, and the arrow's telling us it's going to yield a new row 3. So it can be tedious, but it's very easy to make a small algebra error in these matrices. So when you're starting out, I wouldn't recommend doing this in your head. I'd recommend actually writing things off to the side. So I'm going to take row 3, I'm going to find 3 row 1, and that's going to create my new row 3. So I'm going to add these together to get row 3. So if I pull the numbers from row 3, none of those are going to change. I want to do 3 times this first row. So that's going to give me a 3, a negative 6, a 3, and a 9. Now we just go ahead and add them together. So you get 0, negative 6, positive 2, the bar stays in the same location, and then adding those together gives you 4. So this is going to replace this row 3. So I'm leaving everything else untouched. So my first row is still going to be the same, and my second row is still going to be the same. But my third row is getting replaced by this new one, 0, -6, 2, 4. So these row operations are going to help us to solve these systems. And the method we're going to use is called the Gauss-Jordan method. We ultimately want to get our matrix to what's known as a diagonal form, or you might hear it referred to as reduced row echelon form. The idea is you're going to have a system of 2 equations or 3 equations with 2 or 3 unknowns. You want to get your matrix to this form where you've got a diagonal consisting of 1s and 0s on the off diagonal. And then what's on the right-hand side of the equal sign doesn't matter. It's going to be problem specific. Or if you've got 3 variables, you want to get it to this form, because immediately you're going to be able to pick off your solution. This tells us 1x is equal to A, 1y is equal to B. So the actual solution to our system will be the coordinate AB. In this case, you're going to get the solution as A, B, and C. So x will equal A, y equals B, z equals C. So your system has a single solution. So the best way we can actually go through this is by example. You're going to have kind of an algorithmic process you're going to want to follow. So we're going to start with a 2x2 system, which we do know how to solve using elimination or substitution, but we're going to go through this with a matrix. So the first thing I need to do is write the augmented matrix. My first equation has 3 x's, 2 y's, my constant is -9. My second equation is 2, -5y, and my constant is -6. So the process I want to follow is I need to get it in diagonal form. I want to turn this into a 1. So you got to get a 1 here. You might have to divide by that row by a number. Maybe you can just switch 2 rows. Whatever you can do to get a 1 in this position. In this case, I can't interchange these two because neither of them are 1. So I'm going to take that first row, divide it by 3, and that becomes my new first row. So I take each piece in the first row and divide it by 3. So that'll give me 1, 2 over 3, and then -9 over 3 is going to be -3. My second row, completely untouched. I don't have anything there. Now that I've got a 1 in that position, I need to turn this into a 0 to get that diagonal form. And I'm going to use that 1 in that key spot right there. It's called a pivot spot. So what I need to do is take this number, multiply it by -2, and add it to this one. So the row operation I want to do is -2 times the first row plus the second row becomes my new second row. So for this example, I'm going to go through those operations. I want -2 times row 1. That'll give me -2, -4 over 3, +6. I'm going to add to this row 2, which I haven't done anything with, and that yields my new row 2. So these end up canceling out, and we get a 0 in that spot, which is exactly what we want. The 6 plus the -6 also cancels out, and then -4/3 plus -5 is -19 over 3. So I get my new matrix now. My first row I didn't do anything with, but now I have a new row 2, which is 0, -19 over 3, and 0. Okay. Now I want to work on that 1 in the next spot. So I'm going to turn this into a 1. And so what I need to do is multiply by the reciprocal. So I'm going to multiply by -3 over 19. Leaves the first row untouched. 0 times -3 over 19, 0. Nice stuff happens, and we just get a 1 here because the 19 and the 3 cancel. The minus makes us a positive. And then 0 times negative 3 over 19 is still 0. Okay. The last thing I want to do is turn this into a 0 using that second row, because I can now manipulate this 1 I have right here to make it match but be opposite in sign. So I want to take negative 2/3 times row 2, so that'll make this a negative 2 over 3, add it to the first row, and that'll become my new row 1. So if I do negative 2/3 row 2, I'll get a 0, negative 2 over 3, and a 0. I want to add row 1, so I just copy down row 1. Adding them together gives me a 1, 0, negative 3. And that is my new row 1. So I write my new row 1 here. I did nothing with row 2 itself, and now I have put it in diagonal form. So I can immediately pick off my solution. X is negative 3, y is 0. So x is this, y is this. Or you can write it in that coordinate pair, negative 3, 0. Okay. So it may seem a little bit tedious to go through this process. You can learn shortcuts, you can learn other methods. I'm just going to stick to this one because it's what your book uses. Ultimately, to solve a system of equations, you can choose what you want, but be comfortable being able to write these matrices and performing just row operations in general. But to solve an equation or a system of equations, you can use any method that you prefer. But I am going to show you some more examples, and I'll also show you a case when you have a dependent 3x3 system. So let's try this next one. We've got 3 equations, 3 unknowns. First thing I've got to do is I've got to write that new augmented matrix. So my first equation, I have a single x, a single y, negative z, and a 6. My second has 3 x's, negative 2y, 1z, negative 5, and then 1, 3, negative 2, 14. So my first step is still to turn this into a 1, but nice thing, that's already done for me. If this wasn't a 1, I could have gone and swapped these two, make my life a little easier instead of dividing by a constant, because sometimes that can give you nasty fractions. But now I want to turn this into zeros. So I'm going to turn everything underneath into zeros using that first equation. So what I need to do is I need to take the first row, multiply it by negative 3 to get my new row 2 when I add it to row 2. So we'll go ahead and do that off to the side. If I look at negative 3 row 1 and row 2, we'll add them together. Negative 3 row 1 is negative 3, 1, negative 18. Row 2, we just go ahead and copy down and wrote the wrong things. Now we go ahead and just add them together. So my first row stays completely untouched. My new second row is going to be 0, negative 5, 4, and negative 23. Now I want to work on that third row. So I'm just going to multiply the first one by negative 1, add it to my third row, and that's my new third row. So if we look at negative row 1 and row 3 down here, negative row 1 is negative 1, 1, 1, negative 6. Row 3 is 1, 3, negative 2, 14, and we want to add these together to get our new row 3. So that's going to give us 0, 2, negative 1, and positive 8. So now we're just going to keep repeating this process over and over and over. I'm going to turn this into a 1. And again, you could change it with a third row. I don't want to change it with the first though, because that's going to put a 1 back in a spot I don't want it. So we're going to go ahead and we're going to get a 1 in this position. Easiest way is just take row 2 divided by -5. So we don't do anything with the first row or that third row, but then we go ahead and divide by -5 to give us 1, -4/5, positive 23/4. So you can see it's going to get a little hairy with some fractions, so I'm not going to show every single algebra step. But again, while you're going through it, write down each specific row, add them together off to the side. But now we've got a 1 in the position we want, so we're going to turn everything above and below it into zeros. And we're going to use that second row to do so. So the way we can eliminate from this first piece is I'm going to take negative of the second row, add it to the first, and that's my new first. So my second row doesn't change. When I perform this row operation, we're going to get a 1, a 0, and then if you take 4/5, add it to -1, you get -1/5. 23/5 times -1 plus 6 will give you 7/5. Now if I look at that second piece that I need to turn in that third row, I want to take -2 times the second row, add it to the third row, and there's my new third row. So this will still be a 0. -2 times 1 plus 2 will be 0. -4/5 times 2 plus -1 will give you -3/5. 23/5 times -2 plus 8 should give you -8/6. Okay? So we are almost there. Next step is to get a 1 in that last important position. So we turn this into a 1. And the easiest way is by multiplying by the reciprocal. So multiplying by 5, then dividing by 3. So my first 2 rows don't change. You still get 0, 0. 3/5 times 5/3 is 1. -6/5 times 5/3 will end up giving you -2. And then I've got one more step, is to turn these into zeros using that third row. And then I'll have this in that reduced row echelon form. So I want to take 1/5 times the third row, add it to the first to get my new row 1. And I also want to do 4/5 times the third row plus the second row to get my new second row. So my third row is completely untouched. If I go through this first row operation, we're going to get 1, 0, 0, 1. The second operation will give us 0, 1, 0, 3. And now I can immediately pick off my solution. X is equal to 1, Y is equal to 3, Z is equal to 2. Okay. All right, so let's see how we can see something as a dependent system here, and then we'll look at an inconsistent system as well. So we want to solve this system. And again, first got to turn it into a matrix. So I'm going to pull all the coefficients off and in that X, Y, and Z order. My process is to get a 1 here. So we want to turn this into a 1 by just completely negating the row. So I don't do anything in these bottom 2's, and I just switch the sign of everything in the first row. Now I want to get zeros underneath it. So we want to turn into zeros utilizing that first row. So if I just add the first and second row together, I'll get a 0 in my new second row. If I take -3 times row 1, add it to row 3, there's my new row 3. Okay. So my first row is completely untouched. And if I go through my first operation, row 1 plus row 2, it's my new row 2, I end up with this. My second operation ends up here. So really, you could actually stop here because if you notice, you've got exactly the same equation in both of these, which is going to tell you that you have that dependent system. But if not, you're going to repeat the same process. So you want to turn this into a 1, but lucky for us, it is a 1. So this is done. Then you want to go ahead and turn these into zeros. So it's really nice in this case. If I just add row 1 and 2 together, it'll make that a 0. If I take -2 times row 1, add it to row 3, become my new row 3, I'll get a 0. So these are completely untouched. If I add row 1 and 2 together to get my new row 1, I'll get this. And if I perform this second operation, I'm going to end up with a bunch of zeros down here. And this is our key to tell us we have that dependent system. Remember, this corresponds to an equation. So this last row is telling us 0 equals 0. So we've got a dependent system. Now again, to write these, we have to write it parametrically because there's infinitely many solutions, but again, not every single XYZ combination is going to work in the equation. So I have a free variable, and in this case, I'm going to let z be that variable. It's going to be any real number. If I look at the second row, I've got 1y, -4z, and my constant term. So the second row is telling me y minus 4z must equal -3. Or really, the y coordinate for our solutions has to be 4z minus 3. So if I pick a value of z, this is what y has to be to guarantee I'm on that plane. Now I can do the same thing with this first row. I've got x, z, my constant, and no y's in here. So the first row tells us x minus 5z has to equal -2. Solving that for x, you get x is 5z minus 2. So our solution is my x coordinate has to be 5z minus 2. My y coordinate is 4z minus 3. My z coordinate can be anything we want as long as z is a real number. So this is our way to write that triple system parametrically. Okay. The last thing we're going to do is work on solving an inconsistent system. So that's going to be when there's no solution. So let's go ahead and solve this one by using matrices. So we want to go ahead and turn it into a matrix, pull off all of those coefficients of each in that specific order. Same process, we're going to turn this into a 1, and we're going to do that by just taking every piece in row 1 and dividing it by 2. So that's going to give me 1, -2, 3, and then we have not touched the second row. So same process, I now turn this into a 0. So I want to take -4, multiply it by row 1, and that's going to give me my new row 2. So this one's a little bit easier for me to full write. Let's go ahead. -4 row 1 is -4, 8, and that's going to be -12. If we look at row 2, it's 4, -8, 5. So my first row isn't changed, but when we add these together, we get 0, 0, 7. And that's going to be a problem. This last row is telling us 0 equals 7. So there's going to be no solution to this system. Okay? So the same type of stuff happens. Again, you can use whatever method you want to actually solve a system, but be comfortable with the row operations, be comfortable manipulating them, because we are going to utilize them later on. And we're going to see another way to be able to work with these systems.